Good afternoon, everyone. Hopefully, I'm audible. Okay, thank you. Um, so, we talk a lot about technology and devices that we can use to create a sustainable, decarbonized future. But we don't really talk about what goes into those devices, whether it's your batteries or your solar cells or your fuel cells. The materials that go into the devices that will save the planet are actually causing an extraordinary amount of harm to the planet. That's because making these materials is very, very energy intensive and extremely polluting. I've heard people say that the reason we have industries here is because air quality is really poor in various parts of the world, because we're not manufacturing these materials here. One such material that my lab focuses on is ceramics. So we are looking at developing sustainable methods to synthesize, process, and manufacture materials like ceramics. And the theme of the lab is to look at industrial heat. And industrial heating currently accounts for more than 30% of greenhouse emissions. And any kind of discussion about decarbonization should involve decarbonizing industrial heating. And this is why it matters. We talk about transportation. It's about 30% of emissions if you look at this pie chart. And industrial heating is almost the same amount, but we don't really talk about it much. And where people like me come in is where we talk about chemicals and manufacturing and materials, making materials. That's about 20% of emissions, and that's a lot. And my lab, the specific theme is, can we use electromagnetic radiation to decarbonize industrial heating? And I'll explain to you what all of that means. And we use terms like process intensification. So many times when you're cooking materials or making materials for things like your batteries or other devices, you have large furnaces that are running at temperatures exceeding thousands of degrees Celsius, so something on the order of 10 to 15 to 20 hours. That's a lot of waste of energy, emissions, it's dangerous, right? We are trying to zap these processes so that instead of applying heat for a prolonged period of time, you apply them almost for minutes. The best example is how you microwave things at home. So microwaves are a form of directed energy that can dump a lot of energy, heat, into samples and speed up processes. Sometimes an order of magnitude faster the process can become. And my lab focuses on ceramics because they are almost the non-sexy materials of the world. I mean, we need them for everything. Open up your car, there are millions of these capacitors. Open up your iPhone, thousands of these capacitors. They are ceramics. Extremely stable. They're on space shuttle tiles, automotives, everything. It's a $400 billion industry. None of us think about them. And they are the oldest materials humankind has made. In 15,000 BCE, we were in the caves, we shaped clay, and we put it into fire to make pottery. In 2024, this is pretty much the same approach of making ceramics, where we shape things and we blast it with heat. A very primitive approach for a civilization that is pushing the frontiers of artificial intelligence, right? And these materials are in everything, including our luxury watches and other types of appendages. But when you make these materials, the emissions exceed 2 to 3 times the national average for any of the nasty gases you can think about. And what is the irony here? Every material, including your electrified cars and batteries, contain these materials. So by trying to save the planet, we are going to scale up manufacturing of these materials and essentially close the loop in breaking the planet down, right? We need a different approach to make these materials. That's my pitch, right? So in our lab, we have fun in trying to manipulate processes. And one way to do this is by directed energy deposition. We dump a lot of energy, exactly how you cook in a microwave, into these processes. This is a typical Friday afternoon in our lab. Don't try this at home. Oh, this is what happens if you put metals in the microwave. Everybody tells you not to put a fork in the microwave. I'm telling you, you can go home and do it right now. You'll be fine. You have to make sure there are no paper towels or other stuff, pizzas inside, because the sparks are electrons where a lot of energy has been dumped into them and they have nowhere to go, right? If you have paper towels, the electrons will jump into the paper towels and catch fire. No paper towels, you can do this all day, and we do that in our lab. What's more dangerous is grapes, because if you microwave grapes, this happens. Please go home and try this, okay? I'm not taking any liability, right? I mean, what's happening with the grapes? And this is a real experiment. Grapes are water, right? And microwaves are 2.45 gigahertz, your home microwave. The water in the grape hemisphere is coupled to the microwave, and in the gap, there's an intensification of that electric field. And it's so powerful, a plasma is generated right at the interface of the grapes, and it ionizes all the crap that's in your microwave, and that's the plasma, right? And we have measured the electric fields in that interface, and that's about 10 million volts per meter. It's the order of an electric, a storm, a lightning strike in a storm. So the question is, there's all this energy that is coming out of grapes, right? Why can't we use this energy for decarbonizing some of our hard to decarbonize processes? And a lot of people in my community do that. These are process maps where we can change the time and temperature of various processes shown here in the different colors. And when you apply these various fields, especially microwaves, you're running processes at shorter times and temperatures. Over the years, my group has synthesized an entire library of materials with all of that. The processes are very low temperature, so you can integrate ceramics with polymers, interesting soft electronic applications. You can completely destructure the material to generate a function that is of interest to you. We have a lot of work in understanding dopants and other kinds of disorder that the field generates. Not the topic of interest today. So we create methods of studying these processes. We apply these processes to print large materials, and then we also apply them to industry. These are some examples of large microwave chambers. This is not your home microwave reactor. These things, your home reactor is 1,000 watts, right? We, in under certain conditions, can go up to megawatts and gigawatts with microwaves. Did you know you could do that, right? And with that, we can create large specimens of alumina, yttrium-stabilized zirconia, silicon carbide, other materials. We use almost 95%, 96% less electricity because, try to cook rice in a microwave versus on a stovetop, right? We're tapping into the same dielectric heating physics. We save all this energy mainly because we ramp up to really high temperatures in minutes as opposed to hundreds of minutes. And we also have done extensive work characterizing the process to understand now that for every minute that our material is cooked in the microwave, it takes about 48 to 50 minutes in a conventional system. So this time saving is really where we save on energy. And my wonderful team of students and postdocs have tried very hard to understand what's happening. Very, very briefly, we actually shake atoms out of their sides so they have more space to move around, and that enhances diffusion. And that's why things speed up. We have also used this tech to print materials, all kinds of shapes, and this is an avenue for 3D printing ceramics because you can print metals, you can print polymers. It's extremely hard to print these things. So that's something our explorations have enabled over the years. This did not come easy. We had to understand the complex interrelationships between electromagnetic fields, thermal, heat transfer effects, microstructure, and other kind of materials-related problems in these systems to come to these solutions. And finally, I am now at the stage where we are rolling out some of this into startup companies that spin out of the lab, and we were able to use some of these materials within a lithium-ion battery. And what we found is that a composite version of this material can improve the life of a battery. In this particular case, it makes a battery last about 17 times longer. So that's what my company, Sea Lion, does. And what we think is happening is the specific properties of the material help us protect the ion and keeps it cycling longer. And it's a way for us to contribute to a more sustainable way of energy storage. Instead of having batteries that you throw away, we can have batteries with longer durability, which once they finish their life in something like an electric car, can have a second life in something like a grid or stationary storage application. So I think I should be approaching my 10 minutes. A lot of people and a lot of agencies, both federal and non-federal, including CMU and the Scott Institute, were instrumental in getting all this off the ground, and I'm very, very grateful. If there are questions, I can take them, or else happy to talk. Thank you.
Thanks for the great presentation. I really enjoyed it. One of the challenges with rapidly accelerating material production in terms of heating is often cracking and fractures. You are drastically shortening the ramp time. I'm wondering if you also see more prevalence of cracking.
We do see cracking. And these thermal effects involve a complex interplay between the material that we are trying to heat, the shape of the material, and the sort of intricate features in them. For instance, if a material has more stress points and it's a very complex shape, that's where the crack would initiate and propagate. That said, we have uncovered processes, including additives, that can help us suppress that thermal mismatch in certain material systems.